Okay. Yeah, guys, very good morning to everyone. Okay, today we're going to start the next topic. I think we last class we completed the first chapter. I hope that you don't have any doubt because I asked your doubts in the last end of the last class. Okay, so today we are going to start the next topic. I share my screen slide. Yeah. So are you able to see this slide?
Yes, sir.
Okay.
Yes, sir.
Actually, I shared that yesterday video. Day before yesterday video I shared yesterday in the LMS. Yeah, please go through that LMS. Already I put in the LMS last lecture video. Okay, so today we are going to start this second chapter, design against static load. We are going to study design against static load and dynamic load in the next chapter, and simultaneously we are going to discuss the problems. Which components, machine components, are subjected into static load. Corresponding problems also we are going to discuss in this chapter. When we are going to discuss dynamic load, during that time we are going to discuss corresponding problems. Okay, but in this chapter, before entering inside the content and chapter, we should understand why we are studying this design against static load. Okay, now see here. First, we see the introduction, brief introduction about this chapter. Then we go for the. Then we go inside the topic. See, I have referred some books, and but then I have written my own way. That explanation here, you can directly take it. Simply you can understand this whatever I have written. See here, to ensure our machine components or elements work safety throughout the design life. Right, that is the primary point when we are going to design the new component. That safety is very important. Entire design life of the component, right? And it is very important to analyze the strength under various load. While designing the component, we have to analyze the strength at various load conditions for predicting the potential failures, right, in the early stage of design. Once we identify this, then we can go for the machine component built or for fabrication of the mechanical system. Okay, so that's what it's very important to analyze the strength under the various loads or service loads, and able to predict the failures at the early design stage, well before the machine component or system is built or fabrication. This is the very important. And the third point, to design a element strong enough against failure. How we are going to design, what are the parameters we are going to consider, those things we are going to discuss in the later. But we should identify, while designing the component, we should understand the strong enough against failure due to strength. With the help of the strength analysis, that can be done, right? Then by evaluating the each possible failures, once we know strength analysis strength analysis, for analyzing the strength of the element with the help of strength analysis, then that can be used to evaluate, that can be evaluated each possible of failure with respect to various loads and stresses, various loads or in stresses. Okay, now we are going to discuss the brief introduction about loads, types of loads, and corresponding stresses to be involved in the component. What are the types of loads and stresses? What are the types of loads and stresses are going to be involved when the component is functioning? We are going to discuss. Especially, we are going to give more attention about the static loads in this chapter. Okay, and also we are going to briefly discuss about the fatigue strength, due to cyclic loads. We are going to study later that fatigue strength and dynamic loads in detailed manner, but now we are going to just, if based on time, we are going to discuss about the cyclic loads in very brief manner. Okay. Now, now this is, if any machine power is transmitted from power source, right? Like you can consider the motors or engines, ice engines or two-wheeler or four-wheeler. First the power is transmitted from the main source. The main source may be ice engines. The main source may be motors. For in two-wheelers, the main source is ice engines. The power is transmitted with the help of the chain drive mechanism to the executive components like back wheel. If you consider motor, the motor is connected with the generator or with the compressor. Then the power is transmitted from motor to compressor with the help of the shaft. Okay, that's what we are saying. We are going to study then how much dimensions of the shaft based on the power transmission capacity. That's what we are going to study here. And various loads on driven machines are generally defined in terms of torque or power. Whatever we are transmitting the power from main source to executive components, say like ice engines to back wheel or motor to compressor. We are considering defined in terms of power or torque, right? The design power is obtained by multiplying the service factor with the nominal power transmitted. What is the service factor here? Suppose my requirement is we are doing the new design machine component. Our requirement is transmitting the power 10 kilowatt. That is a nominal power transmission. But as per the design standards, we have to follow certain service factor for ensure the safe limit. My design component is a 10 kilowatt, but I have to multiply with 1.2 or 1.4 or 1.5 or 1.6 or 1.7, whatever may be. We have to multiply with some service factor, then that should be our designed component, designed power. Our normal power transmission is 10 kilowatt. If I multiply with the service factor more than 1.25, then 12.5. 12.5 is my designed power of the component. Why it's required? For safer side, for safe limit. But for safety purpose, we are going to do our designed power always more than the nominal power transmission. But how we are considering the service factor, we are going to see that some standard table, it's obtained from the design data book. Okay, the large service factors allow for high degree of safety of the safety of to account for uncertainties in the design analysis. Where some of for complex structure of the components, we have to give more service factor. Suppose our nominal power transmission is 5 kilowatt, then the service factor we have to consider 2 kilowatt, 2 into 5, 10 kilowatt. So the complex components we should consider the power transmission capacity 10 kilowatt, but actual power transmission is 5 kilowatt, because the complex structure it may failure. We give it because of some uncertainties. Okay, hence we would like to avoid the failure and ensure the safety. We are considering higher service factor for the complex geometry of the components or critical components. What are the critical components? We will see in the table later. The service factors listed in the tables have been calibrated after consider the field experience in particular application and can be used with the reasonable accuracy. The service factor, as you are engineers, right? Now you are directly users. You are engineer now. If you are designing the new component, you are seeing the table, service factor table. You are taking the data from that. But the people who are doing a PG, MTech or PhD, then what they will do? You not only MTech, PhD who are doing R&D sectors, they are validating. They are designing new component. That component they are multiple times they are testing in the field applications. the component they are testing in industrial applications. Then finally, once they ensured that the component working condition good and power transmission capacity, nominal power transmission capacity and maximum power transmission capacity and designed power transmission capacity, once they proved, then they will put it in the data book. Now, as we are in engineer, no, we are UG students. Once you are going for the job, you are directly using the service factor for designing the component or using the designing the existing component, or for manufacturing the existing component, we are using directly from the table. Okay, that's what. From the field experience and industrial applications, we are provided based on that. We are providing the service factor. But how we are providing the service factor based on application, I will show you the table. For the specific elements, the detailed value of service factor can be found from the design handbook or manufacturer catalogs. So what is the service factor? See here. Now, service factor for power transmission. The first thing, the left-hand side is now, this is the power source. 1 minute. This is the left-hand side is power source. For example, I consider electric motor, uniform power source. Electric motor. In the right-hand side, a driven mechanism where the electric motor power is going to be transmitted. The electric motor power to be transmitted to which component? That is in the right-hand side. For example, even the driven mechanism, they are categorizing in 3 methods. One is uniform transmission and light impact, moderate medium impact, and heavy impact power transmission. Okay. Now here, uniform electric motor. This is a power source. Steam or gas turbine. Uniform speed and low torques. Okay. This is the power source also. We are classifying uniform, a light impact, moderate impact, and heavy impact. Now, if I'm using motor for centrifugal compressor, I would like to use, now I'm using motor for operating the centrifugal compressor and uniform power transmission power and light uniform power transmission. Then whatever my nominal power transmission 1 kilowatt, my designed power transmission capacity should be 1.1 kilowatt. I have to design the design the component with respect to 1.1 kilowatt. But now our nominal power transmission capacity, I consider practical power transmission capacity maybe 1 kilowatt. Okay. Suppose if I'm using electric motor for operating the machine tools at a light impact condition. Okay. Now during that time, my power transmission capacity 10 kilowatt, but I have to multiply with the 1.25, then 12.5. I have to design my component 12.5 kilowatt based on 12.5 kilowatt for safety purpose, for safe operation conditions. Okay. Similarly, see here that electric motor can be used for mining machines or heavy machines. Then during that time, I have to consider greater than equal to 1.75. My nominal power transmission capacity may be 100 kilowatt, but our designed power capacity is 175 kilowatt for ensure the safety point of view. Now, heavy impact power source also. Now, single cylinder internal combustion engines are under the heavy impact power sources. But here also, when we are using this mechanism in uniform power transmission, now designed power, our nominal practical power transmission is a 10 kilowatt, but it can be should be multiplied with the 1.5. Then designed power is the designed component with respect to 15 kilowatt. Suppose if we are going for heavy impact utility using this power source, single cylinder or internal combustion engines, then your designed power, your nominal power transmission capacity 100 kilowatt, but your designed component, you should follow the designed component based on 225 kilowatt. Okay, for ensure our safety. Okay, this is the thing. Now we go to the type of loads. You might have been studied, but anyway, this is the content in our second chapter. Now we are going to discuss brief manner it may be very good recollect the information that will help you to solve the problems in the upcoming discussions. Okay, now what are the types of loads? We go briefly. I mean, load is any external force, right? It may be tensile, compressive, whatever may be. The load is any external force, torque, or movement applied to a machine element. The basic form of loads includes like a tension, compression, torsion, and shear or friction, whatever may be, as well as the movements also, right? These are the loads. And to describe the load information, we have to describe the load information. I mean, when the component is working condition or operating condition, while you are designing, I mean, when the component working condition or operating condition, we have to define the load condition about the load information. I mean, the load magnitude, direction, which point of action the load is acting, how much duration the load is acting particular component. We should know before designing the component. Okay, right? And the load, how many number of cycles the load is acting on the particular component, we should know that. Now that, I mean, the analysis and the design of the machine elements, the analysis and design of the machine elements, I mean, involves the extensive stress and deflection analysis. I mean, we are going to discuss, I mean, whatever the components, most of the components, for example, gear design, shaft dimensions, we are going to consider the, I mean, extensive stress and deflection analysis. Based on that extensive stress and deflection analysis, we able to evaluate the dimension of the shaft. So that's what, I mean, the extensive stress analysis, deflection analysis on the foundation or idea of the correct load determination. Correct load determination, as well as this information can be used to define the dimensions of the mechanical component, like a shaft dia, or I mean shaft diameter and hub diameter, for especially in coupling, and key dimensions. Everything we can define with respect to extensive stress and load, I mean deflection analysis. Okay, now based on the loading history, the load applied to an element may be static or fluctuating or shock load, or it may be impact load or random loads. See, what is the static loading, you may know. Fluctuating also, we are going to see what is fluctuating load and impact, and what is random load. Just we see the briefly in the upcoming slide. But in ideal static load, our attention is more in ideal static load in this chapter. Okay, but an ideal static load is applied slowly and it may never removed. Okay, for example, gravity load, based on the component of the weight of the machine or component weight, right? Gravity load is a typical example for this, the static load. Now the load amplitude or magnitude, direction, point of action, we should know. The static load do not change with respect to time, or it may vary very slowly. Okay, but we are almost considering the static load do not change with respect to time in this particularly in this chapter. Okay, the static load can be axial or tension or compression or shear or bending or torsional, whatever we'll discuss later. Okay, combination of these. Okay, I mean, also few machine elements sorry, also the few machine elements are subjected to pure static loads, right? I mean, the static load, based on that static loads, we able to define the dimensions of the machine component. For example, you take simple rod bar, simple square bar or rectangular bar, cross section bar or circular cross section bar. The bar is subjected to pure, I mean, tensile load, axial tensile load. Then with respect to that, stress is load by area. Then stress, you know, maximum stress, how much, what is the maximum stress the, I mean, rod or bar is going to be involved, you know very well. Then stress in the left hand side is equal to P by A, load, you know. Then area, you know, pi by 4 d squared. Then we able to predict what is the dimension of the shaft. That's what the one small simple example I'm Here I am pointing out. Okay. Now the types of loads again further. Now fluctuating loads or variable load. What is fluctuating loads? I mean that the time amplitude, the magnitude of the load varying with respect to time, right? I mean that's what the vary with respect to time during the normal service of the element or mechanical system. I mean, there are typically applied for long duration. So the element experience may many thousands or millions of stress cycles. For example, when your the load may be compressive or tensile, such a manner the load may be acting in the element in long duration or millions of cycles. We are going to discuss especially fluctuating loads, especially fatigue behavior is fluctuating loads. Okay, this is a dynamic behavior. Now, this is here an example is the load acting on the pair of meshing gear teeth. There are two teeth. I mean, this is the engagement, disengagement. This is the teeth. This is a driven driven gear, right? This is a driven gear. The another one is a driving gear. Now, these two teeth. Now, this is the example for when this teeth. This is a teeth 1. This is the driven here D1. This is a driving here D2. Now this is a teeth 1. This is a teeth 2. Now the teeth 1 is engaged to the teeth 2 of the D2 side, right? But this is a teeth 2. This is a teeth 3. Is engagement and disengagement. When engagement, the force the stress is acting on the teeth. When disengagement, it's free from the stress, right? That's what per minute. How many cycles? Based on the speed of the shaft, it will be number of cycles. It can be counted. Okay, that's what we are saying here. Fluctuating and variable loads and the shock or impact loads. The loads applied suddenly and rapidly. For example, force act when car is subjected into crash. Crash analysis very important studies for automobile industries. Okay, crash analysis very important studies for automobile industries. Okay, now that is shock or impact loads. Now we come to the last one, random loads. What is a random load? When the applied loads vary irregularly in their amplitude. For example, wind loads acting in the wind turbine blades, the loads are called random load. Okay, that's what type of loads in different components. So we discuss. Now we move to the types of we enter little basic. Okay, now this is can you tell me what is the stress? Very basic question. What is the stress?
The resistance offered by a material when a force is applied on it.
Yeah. When thank you. When you are applying the load, external load on the material try to resist the external load. That material try to resist the external load. The resistance, where the resistance created inside the material, that is called a stress. Okay, don't tell simply load by area when you are going to have an interview somewhere, placement or government job. Okay, very important. And see here, stress we very well know. There are very very well known. There are important two types of stress: tensile stress, compressive stress. Right? The force Fn, Fs is the normal stress, normal force. This is shearing force. Normal force, normal stress is normal stress. The load, when the load is acting parallel to the axis of the component. Even like this is also wrong. Parallel to the axis of the component in the sense this is axis of the shaft. The load must act in the axis of the shaft, and also the load also parallel to the axis of the shaft, and the load must act on the shaft axis. Then we can say that normal stress, right? Now this is a normal stress, tensile stress. Suppose that two forces are in inward direction. That's in the same axis, in the same orientation. Then it should be a compressive stress, right? But what is the shear stress? The tangential stress is when the load, generally called as shear stress, with respect to tangential force. When the tangential force acting on the machine component, this is the tangential shear stress. Shear stress, I mean, it is applied a force offset from the axis of the component. Offset axis from the component. This is the object fixed. The bottom portion is fixed, but the force is acting here. Right now, what will happen? I mean, this is axis of the component. Now, axis of the component. Now, this is the force is offsetted from the axis of the component, but parallel. But force offsetted from the axis of the component. I mean, in shear force, it's not necessary to parallel to the axis of the component. Okay. Now this is the component going to be subjected into shear. Okay. I take another color. This is shear. Okay. This is the area, sheared area, where the force is acting. This is a corresponding area, sheared area. This is we have to consider for finding the stress in the tensile force, tensile stress. Okay. Now this is, and I mean, we can classify the stress further in the different type. Okay. I mean, uniaxial load, with the uniaxial load, based on uniaxial load, based on biaxial load, based on triaxial load, right? We can classify the stress uniaxial load, biaxial load, triaxial load, right? I mean, I would like to know that, have you studied biaxial load, triaxial load in the strength of material, or only you studied biaxial load? Because I'm not
only biaxial and uniaxial.
Biaxial, okay. Anyway, now we see that just we go through, we have to touch the basics, that we are sure it will help you that. Okay, and see here. Now before entering in that, stress is vector, scalar, or tensor?
Tensor, sir.
How? Yeah, please. Thank you very much. You are good.
It requires 9 magnitudes, I guess, sir.
No, sir. It will have 3 magnitudes, but the direction will be 9. Like one stress will be applied in 3 directions. Similarly, the other 2 will also be applied in 3 directions. Total there will be 9 directions.
9 direction. No, your explanation somewhat okay, but I'm expecting the clarity is not there. No, anyway, thank you very much. At least you told some 60% right answer. I mean, scalar is only magnitude, no direction, right? Scalar. Now see here, force. I mean, scalar, any example? Scalar, example.
Weight of an element.
Yeah, weight of the element. And yeah, exactly. Now, I take here, we have to understand, because now I'm taking quantity. Okay, I'm taking one dimensional, I'm taking 2D, I'm taking 3D, 3 dimensional. Okay, in this, very important, because even when I was there in the last time in placement interview, even some faculty requirement interview, some students, some of them did mistakes in this. Now, because this is easy concept only, but we are forgetting. That is the important. Okay. Now, scalar. Only magnitude, right? Only magnitude, right? In one dimension, I'm going to consider 1 power 0. Only magnitude. Now we are getting only magnitude, right? In 2 dimension, scalar. 2 power 2 is equal to 2 power 0. Sorry. This is also magnitude. No direction, no no direction. When only magnitude means it should be 0. Now in three dimension also, I mean 3 power 0, sorry, here to be 1. Sorry, I did small mistakes. Here to be 1. Here also I did a mistake. Correct it now. 1. This is scalar. Okay. Now I'm going to vector now. Scalar, simply you can say weight. Okay. Now force, I mean vector. Vector, what should be considered? 1 power
1.
1. Okay. 1 dimension. Vector, only one direction. The force is acting with respect to x direction. Okay. Velocity, the vehicle is moving with respect to x direction. only one direction. Now I am taking 2 power 1. 2 is equal to 2 power 1. Okay. Now what is this? I mean, how many forces are acting now? This is, I may tell this is Fx. Can I consider Fx this one? This is Fx, Fy. Okay. Now I come to the next condition. Here how many forces? Here 3 power 1. Here Fx, Fy, Fz. Are you understanding now? Now this is vector. Now stress is, okay, sorry, already I have. Now I come to stress. The thing is, the very important things you missed out. Okay, here stress. How can stress is stress? I mean, this is somebody told that in 9 directions. Stress is also 3 direction only, but how we are going to consider the 3 directional stresses, how we are going to make it a 9 component, we will see now. Okay, now stress, I mean, this is my, okay, I draw a simple diagram here like this. This is my cube. This is x, y, this is z now. Okay. Now what are the things here? I mean, now the force is acting here. Now now this is a sigma. Now sorry, stress is acting here. Now is this notation, is it correct? This notation, is this notation is correct? I mean, correct only, but still, how we should write?
Like on what plane it is applied.
Yeah, exactly. That's what. Now here no plane. In vector quantity only we are considering direction. Hence I am putting 1. Power 1, power 1, power 1. But when we are dealing with the stress, the force, the stress at which plane the stress is acting. Force by area. Which plane this plane is acting. The direction is in x direction. Now this is my x direction. The 2 letters representing that, one is plane, this is representing plane, this is representing direction D. Now I am going to write here, based on that concept I am going to explain here. See, 1 is equal to 1 power 1 power 2. Okay, now 2 power 2 is equal to 2 power 2. Now sorry, here 4. 2 power 2 is equal to 4. Now 3 power 2 is equal to 9. Now you tell me simple tension test. Which category now? How many components will be there based on my table? simple tension test, how many components will be there? One component, right? This. Right? Now come
Yes,
to biaxial stress. Biaxial stress. Biaxial stress, how many components will be there?
4.
Yeah. When we are dealing with, this is sigma x. Now biaxial, thank you, Pa, thank you. Biaxial stress, this is sigma y, this is sigma x, right? This is sigma x. When all are same, I mean, maybe sigma 1 is equal to sigma 2. You might have been studied. I mean, major principal stress, minor principal stress, right? But when all are not, when each stress component not equal, even though when two stresses are playing in the element, this is our element, right? This is some component. When two stresses are playing in the element, obviously shear stress is going to be playing this role, right? Now shear is going to be playing here. Okay, now shear is going to be here. How the shear? This is shear on this direction also shear. I mean, what is another one more? Shear stress. Where it will act shear stress? Where it will act? What is the type of shear? That is what is the shear? That is what is it called? What is called that stress name?
Complementary shear.
Yeah, thank you. Very thank you. This is complementary shear. This, if you put here complementary shear, here this complementary shear. I mean, why we are dealing with all these components? Because any mechanical component functioning or operating during that time, while designing, we should consider mechanical equilibrium. That's what we studied in the first year: thermal equilibrium, mechanical equilibrium, chemical equilibrium. When you are dealing with mechanical equilibrium, we should consider that the component should be mechanical equilibrium, then it should be able to perform the function. Right? Now that's what we are introducing tau, complementary shear stress. Now see here, how many components now here? I write in, I mean, now stress in, okay, scalar vector, okay. Now stress is in what kind of tensor or vector? How can you call it in that? Is it the second order tensor or first order tensor? What is that?
Second order tensor.
Yeah, second order tensor. This one. Now stress in second order tensor. Now the stress is second order tensor. Now we should get to 4 components because this is a biaxial stress. We should get 4 components. Now sigma x, tau x, y, because this guy here is both playing in this both. This is a one couple. This here. This is another couple. Right? Then tau xy. Now tau yx. Tau yx sigma yy. Now this is our tensor in biaxial stress, when the biaxial stress is acting on the component. Right? Now how can I write a triaxial condition? Triaxial condition. Okay, anyway, I make it to. But basic is very important because I mean some of the students may not know about this. I have to spend time in this. Okay. I take just a minute, please. Now I come to the triaxial component, triaxial load. Now triaxial is, now this is, you should understand, as engineer you should understand this tensor. Okay, now this is x, this is y, this is z. Now this is sigma x, this plane is going to be sigma x, opposite direction, this plane is going to be sigma y, this plane is going to be sigma y. Now this plane sigma z, the opposite plane is going to be sigma z. So each plane is going to have, I mean this plane now going to have tau xy, this is going to have tau yx, okay. Sorry, this is yx, plane and direction, sorry. Now this is going to have tau, this is y plane, this is y plane, yx is a x direction. This is this is already we know x plane, here x, no, here x plane, y direction. Similarly here this is the strain, this is the shear stress, tau y x, this is tau xy. Then each, I mean all the phases if you cover, you can write 9 components. What are the 9 components? Sigma xx, sigma zx, y, zx, sigma xx, sigma yy, sigma zz. Okay, now sigma tau xy, tau xy, tau xyx, tau x is tau yx, tau yz, tau zy, tau I mean xz, tau zx. How many components are there? I mean, I have written only these planes. This plane, I tell you, I have written only this plane. Tau, I mean shear stress component. Tau yx, tau xy, tau yx, tau xy. You can write other planes also. Other planes also, tau yz, tau zy, like that. Now, based on the shear equality of shear concept, I mean the PG subject students are going to study what is equality of shears, those things. Based on the equality of shears, I mean we are going to consider these 2 components are I mean okay, first I write this matrix now. Now this is sigma x, now sigma tau y, tau xy, tau xy, tau xz, okay. See tau yx, sigma yy, tau xz, tau zx, right? Am I right? Y.
Sir, it's tau yz,
Tau
in
yz.
second.
Which one? Oh, sorry, correct. Thank you. Here tau yz, tau yz, tau zx, tau zy, sigma zz. Based on shear, I mean cross shears. Based on cross shears, these 2 guys are equal. Based on cross shear, these 2 guys are equal. Okay. Based on cross shear, or these 2 guys are equal. Then I mean totally 6 component going to come. Totally 6 component only we are going to consider finally. But total component is 9. 3 power 2. At a 3 dimension, total 9 components. This is called the stress tensor. Okay. Corresponding strain tensor you are able to write. Now, now we are reducing to 6 component. But this is second order tensor. Second order tensor, right? Stress and strain is second order tensor. Stress and strain are second order tensor. Now, what is this Young's modulus? Young's modulus is nothing but sigma into epsilon. I'm right? Sorry. So what is stress? Sorry, this is wrong. 1 minute.
Stress by strain, sir.
Yeah.
Equal.
Yes. Thank you. Stress by strain. Okay. Now, stress. Then have you? Anyway, just I'm not going in depth, but just for your understanding, I'm going to write this. Now, this is Young's modulus is which order tensor? Have you heard about that? Young's modulus. We can say this simply sigma ij. I is nothing but our plane, j is nothing but our direction. This is a stress tensor. If you write, similarly you can write epsilon ij for strain tensor. 9 into 9 components. Suppose, now I am asking you a small question. Can you tell me the plane stress conditions stress tensor? Plane stress conditions stress tensor. Plane stress condition stress tensor. Stress tensor for plane stress condition. Anyone, please. Arey bus. Z component is 0, na? Plane stress. I give you a clue. Z component is 0. Then this is a plane stress condition. Stress tensor for plane stress condition. Okay, Z component going to be 0. Okay. Now, E is equal to, sigma ijkl. Now I can write sigma is equal to, right? Young's modulus is constant, material constant. Now I can write E into epsilon. But see here, when we are writing, this is how many components now? This one, 9 components we write. We know, right? 9 components, right? Now how many components this now? 9 components. Are you understanding? Now, as per the matrix rule, we have written here the stress tensor in terms of 3 cross 3 matrix. Now, this guy having 9 components, I can write in terms of column matrix. I can write this guy having 9 components, I can write in terms of column matrix. In terms of column matrix, in that sense, sigma xx, sigma, yy, then up to sigma tau xz. Sorry. Tau xz. In between other components will come. This is 1 cross 9. 9 cross 1, right? Row into column. Row into column. 9 cross 1 matrix. Now, here, this is material constant, Young's modulus. Now, how can I write the strain here? Epsilon xx, similarly, epsilon yy, like that. Finally, epsilon xz. 9 component. Right? This also 9 into 1. Then now you tell me, as per the mathematic rule, when we are forming the matrix, then how many components should be there? Can you tell me the rank of matrix? This place, instead of E, how can I write? Instead of E, how can I write here?
9 by
Yeah, 9 by 9 matrix. We should follow the mathematics rule also. Hence, I am replacing this E, but now I am talking about mathematic rule. But even though people are measured. I tell you what it is later. Now, this is 9 cross 9 matrix. 9 cross 9 matrix. Okay, now the Young's modulus we are defining like this: C I J K C C11 C22 like this, C99 like this, some constant. Now simple way I tell you like this, just to keep in your mind, this is not necessary. I mean, anyway, I'm not going deep manner. I mean, sigma I J equal to CFC I J K L into epsilon I K L. Now this 2 is now 9 component because second order tensor. K is K and L is representing second order tensor. I and J is representing second order tensor, 9 component. But as per the mathematical concept, now we are introduced here 9 into 9 cross matrix. Hence, we would like to write here 9 into 9 cross matrix. How many components? 81 components. When you are keeping this 4 at the earlier table, when you are keeping here the 4, 3 power 4, it is going to come 81 components. Hence, we are saying that material constant here, this is the material constant, Young's modulus. Elastic constant is going to be a 4th order tensor. This is 4th order tensor. Have you understood now? If you have any doubt, please ask me. Yeah, guys, have you understood?
Yes, sir.
Okay, guys. Okay, now then I thought to now we move to a few things. Then to remaining things we will continue in the next class. Just 1 minute. Yeah, because we have to go through our based on syllabus. We have to study this. I mean, briefly. We are not going to touch in deep manner. Now see here, the first one is tensile stress, right? Second one is compressive stress. You know very well. Now the third one is shear stress, right? Shear. I mean, this is the force is offsetted as compared to this component, right? Where now this, what kind of failure? I mean, the failure going to happen with respect to shear, right? Now, and that's what the rivet is, single rivet shear. Here, this is before shear, after shear, failure. Now, come to this and see here. Now, this is when we are making washers, we are going for punching operation. The thin sheets with the thin big sheets we would like to make 100 washers. Then the thin sheet going to be would like to cut small washers with the help of punching operation. Then they are also shearing operation. I mean, this surface going to subjected into shearing operation. Okay, these are the now this is the beam. Now the beam is subjected to bending moment, right? Now how we are going to use this concept in our applications? Now here, how we are going to use this concept in our applications? Now this is my shaft. The shaft is supported here. Some bearing support. Both end is in bearing support. Okay. Now the support, the beam. Now the shaft connected with the flywheel, or it may be connected to the pulley. Okay. Now this is connected to the pulley. Now the pulley going to be rotated with the help of the belt drive mechanism. I mean, see here, the motor is connected here. The motor is here. Then the motor is connected with the motor and this motor and the pulley. Now I would like to transmit the power from the motor to this mechanism. This is motor. This is our pulley. Now I'm using flat belt drive mechanism, flat belt drive. Now this is a bearings, bearing 1, bearing 2. This is my shaft. Now what kind of concept we can utilize to find out the dimensions of the shaft here? Can I use simply supported beam concept here? Are you understanding? No? So now we are executing whatever we studied is strength of material, simply supported beam concept. Now we able to use here to design or to define the size of the dimension. What is this? Can you tell me this deflection formula of simply supported beam? Someone tell me what is simply supported beam deflection formula?
W L cube by 48.
L cube divided by 48 EI. Now see here, I know how much load is acting in my belt drive, slack side tension and tight side tension. You know, already studied. Then based on that, how much load is acting? W very well known. Here L is known. About our length of the shaft we know. 48 constant. Material property we know. We know what is I. For I is nothing but, for example, pi d for 4 divided by 64, right? Then now we know the deflection. We are defining the manufacturer. Our deflection should not exceed 0.00 for 0.05 mm, for example. Then that is our tolerance. The shaft should not deflect a point beyond this 0.05 mm. Then that also we are giving here in this side 0.505 mm. Then we know load, we know length of the shaft, we know 48 constant. This is E, material property we know. Now we know diamond, I is, we know the mathematical equation 5d power 64. Now what is d4? We would like to find out based on the deflection analysis. Now I able to find out my dimension of the shaft. Now we are applying this concept, whatever we studied in the earlier strength of material concept here for finding or for defining the dimensions of this shaft. Okay, what is time now? Shall I stop it here?
Yes, sir.
Okay, anyway, I hope that we are going to write speed only, because I compared other sections also. They are also in the same level only. Okay, anyway, in the next class we are going to discuss remaining things. I stop it here. Please wait. I come to the home screen, our meeting screen. Yeah, okay, guys. Still okay. I see that any questions? Yeah, thank you, Karthik. Thank you, Pawan. Okay. Yeah, guys. If you have any doubt, please go ahead. I'm ready to clarify your doubt. Next class we are going to enter a little bit the basics. Then sure, at least one or two classes we need to refresh our basic. Then only we can do clearly in the solving the problem. Otherwise, very difficult. So we will discuss next class also basics, and we try to enter the content also. Okay. In the first second half, at least second half, we try to enter the more core content of this subject. The next class. Okay, guys. If you have any doubt, please go ahead. Otherwise, you can leave the meeting.